Hi everyone. So today we are doing kind of a condensed lesson on inverse functions. Inverse functions is a topic that you looked at last year, so I'm hoping most of this stuff is review for you. However, I did review the practice problems we did today, and there wasn't a whole lot that I felt like I could totally skip over. There was still quite a bit of, people getting things wrong. So definitely going to cover everything. I'll try to talk quickly. Feel free to pause, rewind, all of that kind of stuff if you missed something. So first, just what do I mean by an inverse function? Well, the inverse of a function is something that undoes, which is always a weird word to say, but it undoes something that another function has done. So if one function is designed to add 5 to all of your input values, the inverse would subtract 5 and put it back to where it started. Okay. At its core, anything that you're doing an inverse of is formed by reversing x and y. So when we look down at this example 1 and it gives you just coordinates to find the inverse, and by the way, the notation for inverse is that little -1, I would say something like, well, this first one's still just going to be 1, 1, and then it would go 4, 2, and then 9, 3, and 16, 4. Okay, so all I did was switch all the x's and the y's around. Okay, so describe the relation S and its inverse in words. I just want to know, do you recognize what's going on here? How are these numbers linked together and how are these numbers linked together? And I hope that you're seeing that S is the squaring function. So 1 squared is 1, 2 squared is 4, 3 squared is 9, so on, otherwise known as x squared. Which means that when I reverse it, and I'm turning a 4 into a 2 and a 9 into a 3, really the inverse is the square root function. That's all I was really looking for there. So that's easy when they give you just coordinates to work with, right? But if you're trying to find the inverse of an equation, the inverse of an equation, we're always going to start by switching x and y, and then rearrange to get y back by itself. Now, there are going to be some situations where getting y back by itself is really tricky, kind of difficult. Typically, that occurs when the inverse itself is not a function, and we'll talk about that in just a few minutes. So just know there are going to be some times I'm going to let you slide on this, but if you can solve for y, you should solve for y. Okay? Switch x and y, rearrange, get y back by itself. So when I look down at this example 2, remember that f of x is really like your y, right? So to find the inverse, the very first thing I would do is rewrite this as x equals 6y plus 5. And then I want to dig this y back out of there. I want to get the y back by itself. So I would move the 5 to the other side. So I might say something like x minus 5 equals 6y. And then let's divide by 6. Remember when I divide by 6, both of these things need to be divided by 6. So I would like for you to be in the habit of writing this like this, x over 6 minus 5 over 6. And the reason I say that is if you could actually divide by 6 here, you could do that, but this would still be over 6, and you want to make sure you don't lose track of that 6. Okay. And I mean, technically, if we're writing this as an inverse, if this was originally an f of x, for my final answer, I might say something along the lines of the inverse is x over 6 minus 5 over 6. Okay, but really, even if you just left it like this, as long as you marked that that was an inverse, you'd be fine. Okay, so let's look at that second one. That second one, I think, takes a little bit of work to get it back in terms of y. But so I'm going to start. And I always like to mark that I'm finding the inverse so that if you're trying to follow my work, you don't wonder why suddenly the x and the y flip places. So I have x equals 4 over 3y minus 1. I'm going to take the time to show my steps a little better here. So I can't get y back by itself while it's down here in the denominator. Okay, so I'm going to multiply both sides of the equation by 3y minus 1. So that these two things will cancel. And so now what I'm looking at is an equation that looks like this. 3y minus 1 times x equals 4. And then again, I'm trying to get x alone. Some people might choose to distribute here, but I think that's making more of a mess for us. I think I would rather just divide by x on both sides. Get rid of that. Okay. And so now I have 3y minus 1 equals 4 over x. I'm going to add 1 to the other side. So let's see, I'm just going to keep going down here. So I end up with this 4 over x plus 1 equals 3y. Okay. And then I'm going to divide by 3. And this part might be something you're a little less familiar with. So when I'm dividing this by 3, I need to divide this crazy fraction by 3 and the 1 by 3. When you divide a fraction by something, you can just incorporate that thing you're dividing by in the denominator of the fraction. Okay, so this thing right here, the 4 over x divided by 3, could just become, let's see, I'm going to put the y equals back over here, 4 over 3x, and then plus 1/3. That would be the best way to write that, the kind of simplified way. And again, I could rewrite this as the inverse of x equals 4 over 3x plus 1/3. So really the inverse part is not the hard part. It's the algebra of solving back for y that sometimes can get a little bit tricky. All right, so that problem took up quite a bit of our space there, but we can still get that third problem in here. This one's going to be a little bit easier, actually. So here's my third problem. I'm going to start out by switching x and y. Remember, this is really like y. So I get this. X equals y minus 3. And if I were in the classroom with you right now, I would ask you the question, how do I undo absolute value? Well, if you've taken half a second to think about it, I hope you've come to the conclusion that there is no way really to solve or to undo absolute value. Absolute value doesn't have an inverse operation. We could split this up by doing like a plus or minus, the value of what's inside here, because that's essentially what absolute value is doing. But really, things like this with absolute value, I'm okay with you just leaving like this, okay? So this right here represents one of the exceptions that I would make for having to solve back for y. You can't just start adding 3 to both sides because you've got this inside these brackets here. So the absolute value ones I'm fine with you just leaving in terms of x, okay? But like I said, if you can solve for y, like we did up here, you should. Okay, I'm going to keep moving right along here. Couple of things that you need to know about inverses, and I'm not sure if these are printed in your notes or not, so please, if you're watching this video and you need to pause it right here to write these down, please do. But 2 things you need to know that are pretty important. If 2 functions are inverses of each other, when I do the composite of them, and that's in either direction, I should be left with just x, okay? Just x when I do the composite. And it does have to work in both directions. It's not enough for it just to work in one. And the reason for that is if you think about it, an inverse is meant to undo what's been done. So if you take x and you surround it with all sorts of algebraic stuff, you're adding 5, multiplying by 3, all of those kinds of things. The inverse, when you apply it, is meant to strip all of that away. And so you're left with just the original input value again. Okay? So when you do the composite, it should just equal x. And if you're looking at the graph the graph of one function should be a reflection over the line y equals x. Okay, so we're going to look at both of those things right here with example 3. But again, if you need to write those down, please do, because those are important things. So this says verify that f and g are inverses using function composition, which means what I want to do is I want to find f of g of x. And then in a minute, I'm going to also find g of f of x. So f of g of x would look like this. I'm going to take the g function and plug it into the f function. So I'm going to go 1/2 times 2x minus 8 plus 4. And then I'm going to simplify this. So I'm going to distribute 1/2. So that makes x minus 4 and then plus 4. And then minus 4 and plus 4 cancel each other out, and you're left with just x. Which, remember, if they're inverses, that's what you want to see happen. If I want to be thorough about verifying, I also need to check g of f of x. Now, if this first one hadn't worked, if I hadn't gotten just x, I wouldn't need to bother with doing the second one, okay? But if it worked, then I need to check the other one, and I need to make sure they both work. So g of f of x means I'm going to take the f function and plug it in for x over here. So I'm going to go 2 times 1/2 x plus 4 minus 8. Distribute the 2. And so let's see, 2 times 1/2 x is just x plus 8 minus 8. 8's cancel, and you're left again with just x. I want to point one quick thing out because I know this comes up on your next quiz. A lot of you could look at these two things and probably do this math in your head, right? I get that. But if the question is to verify, it's not enough to just say, I promise I did it in my head. Verify means show, right? So you would want to show that, look, I plugged these into each other and this is what happened, okay? Okay, verify that f and g are inverses by graphing. I will throw those into a calculator real quick, and we'll talk about that. And then I'll probably just sketch them there on my paper. But so in my calculator, let's see, I don't need plot 1 turned on. I'm going to graph the function 1/2 x plus 4. And then my other function is 2x minus 8. Graph. Oh, I got to fix my window. Sorry, that's going to take just a second. Okay. Zoom number 6 is going to fix my window for me. So there's the first function, there's the second function. And remember that if these two things are inverses of each other, they should be a reflection over the line y equals x. Y equals x is a just diagonal line that kind of goes straight up the middle here. So it's like if I fold in my paper on a diagonal. And actually what I think I'll do is I'll graph the line y equals x, but I'm going to change it to be a, I don't know, different kind of line. Let's see. There we go, a dotted line. So, oh, that doesn't look all that different, but this line that just popped up here, this is the line y equals x. So if I folded along that middle line, you would see that this line would lie on top of this line, okay? So that's what you would want to show by graphing. And again, you could do, I mean, really those wouldn't have been hard to graph by hand either, okay? But 1/2 x plus, yeah, 1/2 x plus 4 is going to start like this and be kind of a shallower slope if I'm just sketching here, okay? The other one would be 2x minus 8, so starting at -8, but going up a little steeper, maybe something like that. And then the line y equals x would go straight up the center. Okay, not my best sketch, but you get the idea. Okay, so that's what I mean when I say verify by graphing. And I would be fine if this question were on your quiz with you doing that on your calculator, but I would want you to show me what that graph looked like. Okay, so example 4. Are these two things inverses of each other, and how do you know? And you know, you may want to look at this and say, well, I think those two things would reverse each other or something like that. But remember, the real way to know is what we wrote down back here. Okay, if I'm trying to prove or disprove, this is what I want to focus on. Mathematically, this is how I can justify or find a counterexample. Okay, so if I want these two things to be inverses of each other, we should be able to do f of g of x and have it come out to just equal x. Okay, So f of g of x would be x to the power of negative 2 squared. And so then the question is, do these two things cancel each other out? They do not, because when you raise a power to a power, you multiply. So this would become x to the power of negative 4, okay? And so I would say, no, these two things are not inverses, which means I don't need to bother checking the other one, right? The other thing I could do, if I really wanted to, is graph these two things. So I could graph x squared and x to the power of negative 2 and take a look at these things on the graph. So there's my friend x squared, the parabola, okay? Here's x to the power of negative 2, okay? Clearly those two things are not a reflection over that diagonal line. And I know it's hard to tell one from the other. Let me darken this one in. There we go. Okay, so there's x squared. There's x to the power of negative 2. Almost looks like a hyperbola. Technically, it's called something different, but same idea with the asymptotes and everything. But if you drew that diagonal line in, definitely these two things would not be, I mean, the shape isn't even the same. So nope, not inverses. Okay, one more quick thing. The horizontal line test, and I never like teaching this, to be entirely honest, because I worry that we'll get it confused with the vertical line test, okay? But what the horizontal line test is meant to tell you is check to see if a function's inverse will be a function. And I'll show you what I mean by that in just a minute. Okay. So here's the thing with inverses. You can start with something that is a function, find the inverse, and have it not be a function anymore. Or you can start with something that's not a function, and when you find the inverse, it suddenly becomes one. Or you could have a function, and it could stay a function. Okay? So just because something is a function doesn't necessarily mean its inverse is a function. So as an example, okay, and I think this same example comes up down below, but if I were to look at, I'll get creative here. Let's do a trig graph. This is the graph of the sine function, okay? And this right now is a function, okay? If I asked you to justify knowing that this graph I just drew is a function, okay, you could tell me it's a function because of the vertical line test, right? So what the horizontal line test does is it says, well, hey, look at this. When I draw a line this way, I hit the graph multiple times. That doesn't mean that this thing is not a function, but it means that if I were to find the inverse would not be a function. So the inverse, if I were to draw it, would kind of look like this thing sort of flipped on its side. It'd look, gosh, I didn't do a good job with those bumps might not line up correctly, but it would look something along those lines, okay? And you can see that now that I've drawn the inverse fails the vertical line test, okay? So we would say not a function. Because this fails the vertical line test, right? So the horizontal line test is meant to save you from having to actually take the time to draw the inverse. You're supposed to be able to look at something and say, oh, well, because I can see that horizontal line, when I flip it, I know that the vertical line test will suddenly kick in, okay? So if I were to give you something like these problems down below, oh, look, I gave you a trig function down there too. Not as creative as I thought, I guess. But if I were to give you something and say, is this thing a function, or is its inverse a function, you could justify it by saying no, because I can tell from the horizontal line test that it won't be. Or you could justify it by saying, hey, I went and drew the inverse and it fails the vertical line test. The thing you have to look out for is you have to be really specific about which test you're using on which graph. If I were to ask you a question like that and you were to say no, fails vertical line test, I don't know if you're talking about the original or the inverse, okay? And same with horizontal line test. So you're going to want to make sure that you're really specific in your answers about the original function fails the horizontal line test, or the inverse function fails the vertical line test. Okay? Okay, so first these just say tell if each graph represents a function. So just real quickly, vertical line test, this would be a function, right? This would be a function. This would be a function. This would not be a function. I did that just thinking vertical line test on all of those red lines, okay? So now let's talk about the inverse, all right? And I'll use the orange to represent the inverse. If I do the horizontal line test here, this is going to hit twice. So I know that if I were to flip this thing over and find the inverse would not be a function, okay? This one, however, I could draw horizontal lines all day long and never hit the graph more than once. So this one, even if I were to find the inverse, it would still remain a function, okay? And I could justify that, again, by saying pass the horizontal line test. Okay, the original graph passed the horizontal line test. This one we kind of already talked about, right? Kind of the same situation as up here. If I were to do this, I hit multiple times. So the inverse would not be a function. Okay. This thing is not a function right now, but I have no issues with that horizontal line test, right? There's nowhere that I'm going to hit more than once. So if I were to find the inverse would in fact be a function. Really, this is the inverse of this thing. So that's why you see this kind of back and forth relationship. So, like I said, the biggest thing I want you to take away from this is that you've got to be real specific in your justifications. Are you talking about the original graph, or are you talking about the inverse graph? Because you could go either way. Okay, I think that's everything I wanted to say on inverse functions. Let's give the homework a try, and we'll see if you run into anything you need help with. Homework for tonight would be section 3.8, I believe. Is that what section this was? Yes, 3.8 from the textbook, and I will see you Monday.